106 meters. That is deeper than most humans will ever go beneath the surface of any sea. It is deeper than the height of a 30-story building, inverted, pointing down into darkness and crushing pressure. And at that depth, beneath the most strategically vital stretch of water on Earth, someone decided to build a road. Welcome back to the channel. What you are about to see is one of the most audacious and technically demanding road tunnel projects ever attempted by human engineering. This is the Eurasia Tunnel, the underwater highway that connects Europe to Asia beneath the Bosphorus Strait in Istanbul, Turkey. This is not just a tunnel. It is a two-level stacked road system, one lane traveling in each direction, buried more than 100 meters below the surface of one of the world's busiest shipping lanes, in a city that sits directly on some of the most seismically active fault lines on the planet. This is not just infrastructure. This is a defiance of geography, geology, and physics, engineered into reality over 5 years of relentless construction. Imagine the obstacles. A strait with ship traffic so dense it barely pauses. A seabed geology that shifts and surprises at every drill. Strong underwater currents. A city of 15 million people living directly above the work zone. Earthquake risk that could rattle the entire structure at any moment. Visibility near zero beneath the waterline. Water pressure that increases with every meter of depth. Ancient ruins potentially buried in the silt. Environmental protections on both the European and Asian shorelines. And a requirement that, throughout all of this, 48,000 ships per year continue to pass overhead without interruption. They decided to build the road anyway. Before we continue, make sure you subscribe to the channel and hit the notification bell so you never miss a new video. And stay with us until the end, because what engineers discovered at the bottom of the Bosphorus, 100 meters below the surface, will change the way you look at every road you have ever driven. At first, there was only the water, the Bosphorus Strait, narrow, ancient, relentless. No tunnel, no crossing, no connection at the seabed level. Just the deep, cold channel that had separated the European and Asian halves of Istanbul for all of recorded history. On the surface, 2 great suspension bridges had been built. The first in 1973, the second in 1988. They were engineering achievements in their own right, but they were not enough. Istanbul had grown into one of the world's most densely populated and heavily trafficked cities. The bridges were overwhelmed. During peak hours, crossing the Bosphorus could take more than an hour. A city straddling 2 continents was being strangled by its own geography. If you built more bridges, you added more approach roads through an already congested city, and the bridges themselves would still be vulnerable to weather, accidents, and the infinite pressure of daily traffic. If you built a railway underwater, which Istanbul had already done with the Marmara Rail Tunnel, you moved commuters. But you could not move cars. You could not move trucks. You could not move the freight and commercial traffic that the economy of a 15 million person metropolis demands every single day. The problem was not one of will or money alone. The problem was physics, depth, and the extraordinary hostility of the environment below. So the solution was not a simple bored tunnel through soft ground. It was a hybrid system, part immersed tube placed in a dredged trench on the seabed, and part bored tunnel sections cut through the rock and earth of each shoreline. 2 different construction techniques, 2 different geological environments, 1 continuous passage stretching 14.6 kilometers in total. And that passage would carry not 1 road, but 2, stacked on top of each other. 1 level for Asia-bound traffic, 1 level for Europe-bound traffic, inside a single tube at the bottom of the sea. The joint venture of SK Engineering and Construction from South Korea and Yapı Merkezi from Turkey was awarded the project. Work began in 2011. The clock was running. Then came the surveys. Before a single piece of equipment entered the water, the engineering teams needed to understand exactly what lay beneath the Bosphorus. This was not simple cartography. This was forensic investigation of a seabed that had never been mapped at this level of detail. Specialist survey vessels swept the strait with sonar equipment, multi-beam echo sounders, sub-bottom profilers, side-scan sonar arrays, current measurement instruments, sediment coring rigs, and geophysical sensors that could read the composition of the ground dozens of meters below the seabed surface. The teams were looking for fault lines, unstable sediment pockets, ancient river channels buried in the silt, archaeological deposits. Istanbul has been continuously inhabited for thousands of years, and the seabed holds its history. They were mapping water current patterns, tidal variations, and the interference patterns created by the constant parade of ships above. What they found was not reassuring. The Bosphorus is not a simple channel with a flat, predictable floor. Its seabed is layered, a complex stratigraphy of different soil types, rock formations, and sediment deposits accumulated over millennia. In some zones, the ground was firm. In others, it was soft, compressible, and prone to shifting under load. The current patterns were more complex than any surface chart had suggested. Layered flows moving in different directions at different depths, driven by the salinity difference between the Black Sea and the Marmara Sea that the Bosphorus connects. And beneath the sediment, the archaeological sensitivity of the site was significant. This was the ancient seabed of a city whose history stretched back thousands of years. Every measurement mattered. Every anomaly mattered. Because at this depth, a surprise underground is not a delay, it is a catastrophe. Then came the dredging. Before any tunnel element could be lowered to the bottom, the seabed had to be prepared. A trench had to be cut through the floor of the Bosphorus with surgical precision. Not too wide, not too narrow. Deep enough to accept the tunnel sections and still leave adequate rock and sediment cover above them. Specialist dredging vessels worked in the middle of active shipping traffic. They operated around the clock, day and night, in conditions that ranged from flat calm to rough, in currents that pushed against every movement, in waters so turbid that visibility from the surface gave no indication of what the equipment was actually doing on the seabed below. The dredging operation removed enormous quantities of material, sediment, rock fragments, accumulated debris from centuries of maritime activity, and in some locations, material that had to be handled carefully because of its archaeological sensitivity. The trench floor was then leveled and prepared to receive the gravel foundation bedding on which the tunnel elements would rest. This bedding layer was placed with extraordinary care, because the tunnel elements sitting on top of it had to be leveled to within millimeters. An uneven foundation transmits uneven stress into the tunnel shell. Uneven stress in a concrete structure at the bottom of the sea, in an earthquake zone, is a problem that cannot be corrected after the fact. The dredging vessels removed material. Survey divers and remotely operated vehicles inspected the result. Adjustments were made. The process repeated until the foundation was exactly right. Then came the construction of the tunnel elements themselves. The immersed tube sections, the segments that would form the underwater portion of the tunnel, were not built at the bottom of the sea. They were built on land, at a fabrication yard, away from the chaos of the Strait. Enormous concrete tunnel segments were prefabricated as rectangular shells, each one a self-contained section of the future road, designed to exact dimensional tolerances that would allow them to connect seamlessly on the seabed. The fabrication process was a construction project in itself. Steel reinforcement cages had to be assembled first. Intricate three-dimensional lattices of rebar that would give the concrete its tensile strength and its ability to absorb the bending and twisting forces that the tunnel would experience over its lifetime. These cages were assembled by hand, tied and welded into position with millimeter precision, because the concrete poured around them would be permanent and irreversible. Then came the formwork, the temporary molds that gave each element its shape, set up to tolerances tighter than most above-ground construction ever demands. Then the concrete pours themselves, carefully controlled for mix design, water-to-cement ratio, admixture dosing, and pour rate, to ensure that the finished shell was dense, strong, and free of the internal voids and cracks that would compromise its waterproof integrity. Each element required weeks of curing time before it could be moved. During curing, the elements were monitored for shrinkage cracking, surface defects, and dimensional compliance. Any deviation from specification had to be addressed before the element left the yard. Then came the waterproofing. Multiple layers of membrane applied to the exterior of the concrete shell, each layer inspected before the next was applied. because the waterproofing system was the primary barrier between the tunnel interior and the Bosphorus. Then, the ballast systems. The internal ballast tanks and external ballast weights that would control the element's buoyancy during the immersion operation, allowing it to be sunk at a controlled rate without free-falling to the seabed. Then, the temporary end caps that sealed each element during towing and immersion, keeping it watertight until the moment of connection. Every detail mattered. Every step was inspected and documented before the element was cleared for immersion. Then came the immersion. This is the phase that looks, from above, almost impossibly calm, and is, below the surface, one of the most technically complex operations in construction engineering. Each prefabricated tunnel element was towed out of the fabrication yard and into the strait by tugs, moving slowly, carefully, under the watchful attention of marine coordinators managing the traffic of the world's busiest waterway around the operation. The towing route had to be coordinated with the Turkish maritime authorities to create temporary exclusion zones that kept commercial shipping clear while the element was maneuvered into position. Once in position above the prepared trench, positioning barges fixed to the element held it in place against the Bosphorus current. Ballast tanks were flooded gradually to begin the descent. The element sank slowly, meters per hour, not meters per minute. Guided by GPS positioning systems accurate to centimeters, survey wires tensioned from the surface to anchors on the seabed, and remotely operated underwater vehicles with high-definition cameras transmitting live footage to the control room on the surface barge. The engineers watched their screens. They could see the element descending. They could see the previously placed element waiting on the seabed. They could see the target position marked by survey markers on the trench foundation. They adjusted the ballast rates to maintain level. They used thrusters on the positioning barges to correct for current drift. They communicated in real time with the dive teams working below, who provided a second set of eyes on the alignment as the element approached its final position. Then, with extraordinary gentleness, each element settled onto its gravel foundation bed, and the survey systems confirmed whether it had landed within the required tolerance. At this depth, with this weight, with these stakes, within centimeters was the only acceptable answer. Then came the connection. Once an element landed on its foundation, divers and remotely operated vehicles worked to align it precisely with the previously placed element. A temporary rubber gasket, the Omega seal, was positioned at the joint face. The water trapped in the space between the two element ends was pumped out, creating a pressure differential. The immense force of the Bosphorus pressing against the outside of the tunnel compressed the elements together, crushing the Omega seal into a watertight barrier. The seal held. The engineers confirmed the pressure readings. The interior of the connection space was now dry enough for workers to enter. Workers came in through airlocks, human beings walking through a fresh connection point between two segments of a tunnel at the bottom of the sea, sealing the permanent internal joint from the inside. They installed the permanent waterproof joint seal, bolted the connection flanges, applied the sealant layers, and inspected every centimeter of the interface. Then, the temporary end cap on the new element was removed, opening the completed section of the tunnel to the sections behind it. Another segment was joined. The tunnel grew. Element by element, joint by joint, the underwater road extended across the Bosphorus floor. Then came the bored sections. At each end of the immersed tube, where the tunnel transitions from the underwater portion to the underground approach beneath each shoreline, tunnel boring machines were deployed. These machines are extraordinary in themselves. Rotating cutting heads, meters in diameter, that grind through rock and soil while simultaneously erecting a lining of precast concrete segments behind them, sealing the excavated space before the ground can move. The machines at each end of the Eurasia Tunnel bored through the geological formations of the European and Asian coasts, connecting the submerged section to the surface road network on each side. The geology at each end was different. The European side presented one set of soil conditions and rock types. The Asian side presented another. The boring teams encountered varying rock hardness that required constant adjustment of the cutting head speed and thrust pressure. They encountered groundwater infiltration points that required grouting, injecting cement or chemical grout into the surrounding ground to seal water pathways before the machine moved forward. They navigated the boring machines beneath Istanbul's urban fabric, beneath streets, beneath building foundations, beneath utility pipes and cables installed across multiple centuries of city development. Throughout the boring operation, a dense network of surface settlement monitoring points was maintained above the tunnel line. Any movement of the ground surface, measured in millimeters, was detected, analyzed, and responded to before it could become a structural problem for the buildings and infrastructure above. Then came the interior fit-out. Once the tunnel shell was complete, immersed sections joined, bored sections connected, the full 14.6-kilometer alignment sealed, the construction of the actual road began inside. This phase was vast in its complexity. 2 road deck levels had to be built inside the tube. The upper level deck for one direction of traffic, supported on columns rising from the invert of the tunnel, and the lower level road on the tunnel floor itself. Between and around these decks, a full set of life safety and operational systems had to be installed. The longitudinal ventilation system with jet fans capable of managing exhaust concentrations and smoke during a fire event. The transverse drainage channels collecting road runoff on both levels. The fire detection and suppression system covering every meter of both carriageways. The emergency escape routes connecting both levels at regular intervals and leading to safe egress points. The closed-circuit television network monitoring every section of both levels in real time. The variable message signs and overhead lane control signals guiding drivers and communicating emergency instructions. The traffic detection loops embedded in the road surface tracking vehicle counts and speeds. The public address system for emergency announcements. The radio rebroadcast system ensuring that emergency service radio communication functions inside the tunnel. The emergency lighting independent of the main power supply and capable of sustained operation during a power failure. The tunnel control system integrating every sensor, every camera, every alarm, every control actuator into a unified operational platform, monitored continuously from a surface control center. Every system mattered. Every system was designed not just to function normally, but to function during an emergency. Because a tunnel emergency at the bottom of the Bosphorus is not a situation in which any system is allowed to fail. Then came the earthquake engineering review. Istanbul's seismic risk was not treated as a background condition in the design of this tunnel. It was the central structural challenge that shaped every decision from the ground up. The flexible joint systems between immersed tube elements were designed to accommodate relative movement between adjacent sections during a seismic event, allowing the tunnel to flex rather than fracture, to absorb seismic energy through controlled movement rather than catastrophic cracking. The amount of movement each joint was designed to accommodate was calculated from the seismic hazard analysis for the specific location of each joint on the seabed. Different joints had different allowable movement ranges based on their depth, their proximity to known fault structures, and the soil conditions surrounding them. The structural reinforcement of the tunnel shell itself was designed to resist the additional loads imposed by seismic accelerations in both the horizontal and vertical directions. The foundation preparation on the seabed included measures to prevent liquefaction of the surrounding sediment, a phenomenon where saturated soils lose their strength during an earthquake and behave temporarily like a liquid, potentially destabilizing any structure founded in them. Then came the testing phase, comprehensive, methodical, and uncompromising. Every major system in the tunnel was activated and validated before a single vehicle was permitted inside. Fire suppression systems were triggered in test scenarios to confirm coverage, response time, and suppression effectiveness. Ventilation performance was measured under modeled traffic conditions, including simulated fire events where the ventilation system's role is not just to remove exhaust, but to control smoke movement and maintain a tenable atmosphere in the escape routes. Emergency lighting was tested under total main power failure conditions. Structural monitoring sensors, embedded in the tunnel shell during construction at hundreds of locations, were read against baseline values to confirm that the as-built structure matched the design model. The traffic management and tunnel control systems were subjected to simulated failure scenarios to confirm that backup systems activated correctly and that the human operators in the control center could manage degraded mode operations. Emergency services conducted live exercises inside the tunnel before opening. Fire brigades, ambulance services, and police working through realistic incident scenarios to confirm response times, communication reliability, and the operational effectiveness of the emergency systems. The tunnel was inspected joint by joint, meter by meter, for waterproofing integrity, surface defects, drainage function, and compliance with the geometric tolerances specified in the design. Pavement quality was assessed. Lane marking geometry was verified. Every overhead gantry and signal was tested. And when every item on the verification list had been signed off, when every engineer, every inspector, and every authority had confirmed that the tunnel met its specification, the Eurasia Tunnel opened to traffic on December 20th, 2016. Most drivers who use the Eurasia Tunnel today enter a well-lit road, merge into their lane, and emerge on the other side in approximately 15 minutes. They do not see the years of survey work that mapped every meter of the seabed above which they are traveling. They do not see the trench, cut with precision into the floor of the Bosphorus, that holds their road in place. They do not see the immersed tube elements, those enormous prefabricated concrete shells sunk one by one into position, each one joined to the next in an act of engineering precision performed at the bottom of the sea. They do not see the flexible seismic joints designed to allow the tunnel to move without breaking, absorbing the energy of an earthquake that may or may not come, protecting the road and everyone on it. They do not see the ventilation systems pushing clean air through sealed chambers 100 meters below sea level. They do not see the drainage channels, the fire suppression pipework, the embedded sensors reading pressure and moisture and structural strain at thousands of points along the tunnel shell. They do not see the remotely operated vehicles that guided each element to within centimeters of its target on the dark seabed. They do not see the divers who confirmed each seal, in water where visibility measured in centimeters, under pressure that compresses the body in ways that demand absolute respect. They do not see the fact that beneath their wheels, beneath the asphalt and the road deck and the concrete shell and the gravel bedding and the trench floor, is the Bosphorus Strait, one of the world's busiest waterways, still moving above them, still carrying its 48,000 vessels per year, entirely unaware of the road that passes beneath it. This was not infrastructure. This was a negotiation with geology, with physics, with seismology, with maritime law, with the history of a city built on 2 continents. The engineers who designed it understood something profound, that the hardest part of connecting 2 continents is not the crossing itself. It is understanding exactly what lies between them. The builders who constructed it understood something equally profound, that at the bottom of the sea, in the dark, under pressure, in the cold, every detail either holds or it doesn't. There is no middle ground 100 meters below the surface of the Bosphorus. The Eurasia Tunnel does not announce itself. It does not dominate the skyline of Istanbul the way the great suspension bridges do. It is invisible from the surface. It is quiet. It is, in the most literal sense, hidden. And perhaps that is exactly the point. The greatest feats of engineering are not always the ones you can see. Sometimes they are the ones that carry you through the impossible and deliver you to the other side before you have had time to appreciate just how extraordinary the journey was. If you enjoyed this video, subscribe to the channel and leave a comment below. What mega project do you want us to cover next? Thank you for watching.